lesson. Okay, right. For kinematics, the chapter is mainly about the study of motion. Okay, and when you're talking about the motion here, you don't really bother about the forces that cause the motion. That one will be for the following chapter under dynamics. Over here, you're only concerned with the motion of an object. And when we talk about the motion of an object, you want to describe its motion, usually you talk about three things. Number one, how far has it moved? And then number two, how fast is it moving? And then number three, is it speeding up or slowing down? So these are some of the things that you are interested in when trying to describe the motion of an object. How far has it moved? How fast is it moving? And then whether is it speeding up or slowing down. When you want to describe the motion of an object in terms of these three criteria, there are specific physical quantities that you will use. The first one that you will use is actually, let me just zoom in first. Okay, the first physical quantity that you will learn is something called distance and displacement. Okay, distance and displacement. Distance and displacement tells you how far something has moved in layman's term. And then distance is defined as the total length traveled by an object irrespective of its direction of motion. Whereas we will tell you displacement is the distance from a reference point in a specific direction. So if I give you an example right now, you have point A and then you have point B. You want to go from point A to point B. One person took this path to go from point A to point B. This is what you call as distance, the total length traveled from one point to another, irrespective of the direction. You don't really bother about the direction, you just really bother about the total length you have traveled. But on the other hand, when you're talking about displacement, displacement is the distance from a reference point in a specific direction. In your case, your reference point is always the starting point. Okay, so the displacement is this pink colored highlighted line here. Okay, it is defined as the distance from a reference point in a specific direction. Your reference point being point A here, your direction being towards here. This is what you call as displacement. Now, displacement in some cases would have been described as the straight line distance between 2 points or the shortest distance between 2 points. They're basically the same thing. They could also refer to displacement, but in your exams, when they ask you to define displacement, this is the common definition that you will use. No doubt that this definition also can be used to describe displacement, but this isn't the formal definition that they use in your exam marking scheme. The formal definition is this one, okay? Distance from a reference point in a specific direction. It also does mean that it is a straight line distance between 2 points or the shortest distance between 2 points. When you're talking about straight line distance between 2 points, that is already the shortest distance possible, okay? So they're actually the same thing. But just don't use this when you're being asked to define displacement. Okay, so distance and displacement both have SI unit in meters, but distance is a scalar because you don't consider direction, whereas displacement is a vector because you consider direction inside. Now, in some cases, you could have a motion where you say that there's zero displacement, but there is distance traveled. An example would be the ones that you see here. Consider a runner that is completing one lap on a running track, and the man starts and stops at the same point. So that man starts from here, he moved one lap, and then ended up where he started before. If we ask you what is the distance, it will just be 10 meter plus 5 meter plus 10 meter plus 5 meter, giving you 30 meter. In this case here, we just don't bother about the direction of motion. But if we were to ask you what is the displacement of that person from start to end, we will say that his displacement is 0 because your starting point and end point are both at the same point. there's no distance from it in any direction. So the displacement here is considered to be 0. So you could have cases where you have distance, but no displacement. This is one case. Then after that, maybe you have some other cases like this, where we tell you an object travels from A to B and then to C. The first example is this one here, goes from A to B and then to C. Here we will say that your distance is just 6 meter plus 8 meter, giving you 14 meter. But when we ask you about your displacement is actually the distance from a reference point in a specific direction. It's the straight line distance between the 2 points. This is your reference point. It is always going to be the starting point. Okay, so this is your displacement. Your displacement here is 10 meter. How you got the 10 meter was by using Pythagoras theorem, because you assume that this is a right angle triangle. So this side here would be equals to the square root of 6 square plus 8 square, giving you 10 meter. So this is displacement. Then if you have another case where you have an object that moves from point A to B, and then the person made a U-turn in the opposite direction and move in the opposite direction. Right now we ask you what is your distance traveled. Your distance will just be 4 meter plus 12 meter, giving you 16 meter. But on the other hand, when we ask you what is your displacement from reference point, this one being your reference point, is to the final point is going to be this one. Okay, it's going to be this line here. Let me just highlight it. So this is your displacement. This displacement is actually going to be 8 meter. And then is a negative because it's on the other opposite side of your reference point. This side here will be considered as your positive displacement. This side here will be considered as your negative displacement. So here, the total length is actually 8. It's negative 8 meters. All right, there's a way for us to determine what is positive or negative. That one I will elaborate more towards the middle of the chapter. But just know that for now, this displacement is negative because we assume that the side above, because we assume that this side here is positive. So the opposite side here must be negative. Okay, right, so this is distance and displacement. Okay, so when you're talking about displacement can always be found from your velocity time graph. Let me clear everything off. Displacement can always be found from the area under your velocity time graph. Okay, similarly, you can also say the distance moved can also be found by calculating the area under your velocity time graph. Okay, they are interchangeable. So in the cases here where you have few velocity time graphs, these are some of the examples here. Specifically, this one, right? So like for all of this, to find the area under the graph, if you find the area under the graph, all this will give you your displacement or distance traveled. All right. There are some cases where you will notice that your velocity time graph has values above your x-axis as well as below your x-axis. Now, in that case, the area under the graph will actually represent two different things. Okay. So if, say, you have area above your x-axis, it will represent distance moved in one direction. When you have another area under the graph that is below the x-axis, like this one will represent to you the distance moved in opposite direction. Okay, so when you have a graph where you see that they are both positive areas and negative areas, basically you see an area above and below your x-axis, that's telling you that your object is actually moving in two different directions. The part where you see the area above the x-axis, it will tell you distance moved in one direction, and then the area under the x-axis it will tell you distance moved in the opposite direction. Okay, so I already rotate that. Area below your axis actually represents distance moved in the opposite direction. The same case can also be said for the second diagram over here. Okay, this is distance moved in one direction, and then this one is distance moved in the opposite direction. So that is that. Okay, then this is just for distance and displacement. We also have something called speed and velocity. Now, speed and velocity basically tells you how fast you're moving. All right, so speed and velocity tells you how fast you're moving. Again, there's two terms here. Speed is just distance traveled per unit time, measured in meter per second. Now, in the event that the speed is not constant, when say the object moves from point A to point B, and the speed is not constant, you will normally use the term average speed, calculated over a period of time, over that distance. Okay, sorry, over that time and over that distance. So what you will do is that average speed is actually total distance over total time then. If it's just speed itself, it's just distance divided by time. But if you're talking about average speed, it's total distance over your total time. And then after that, velocity v is the rate of change of displacement, again measured in meter per second. So same thing again here, if your velocity is not constant, you will need to use something called average velocity calculated over a period of time. So velocity is rate of change of displacement, is going to be delta s over delta t. Average velocity will be total displacement over total time. Okay, now speed is a scalar quantity, there's no direction to consider, but velocity is a vector quantity because you have direction to consider. So one thing to see from here would be, let me just go to the third page. Okay, so there's some example in the next page to illustrate what I'm saying about. Now, you have a runner that covers one lap of a circular track in 14 minutes. Sorry, one lap of a circular track, 40 meter in diameter in 62.5 seconds. For that lap, what is her average speed and her average velocity? So you have a runner that's moving in one circle like this. Okay, and they tell you that the circular track is 14 meter in diameter, and the runner took 62.5 seconds to complete one lap. Okay, right now you're supposed to calculate out the average speed and the average velocity. Now, based on the definitions for average speed just now, average speed is actually total distance divided by total time. Now your total distance here is actually the circumference of your circle. So circumference of a circle is actually just pi d. Okay, pi d divided by t now. So this one will be pi times with 40 divided by 62.5. You will get this answer. Let me just calculate that quickly. Times 40 divided by 62.5. You should get the answer as 2.01 meter per second. Now, on the other hand, if you want to calculate out the average velocity based on the definition in the previous page, it will be total displacement over total time. Now, in the case where you have a runner that ran a full lap in a circle and returned back to the same original point where she started off with, your total displacement is actually just going to be 0. So although you are taking some time to move one round, your total displacement is still considered to be 0. So eventually your average velocity is just considered to be 0. Okay, so there's a difference between this and this right now. average speed has some value here, but average velocity has no value. It's just zero. Okay, so average velocity can be zero when the total displacement of an object that is moved is zero. Just like the earlier example just now I told you, when the runner runs through a full lap, the runner can have a distance traveled but no displacement. Okay, now then the next example, you have an object that travels from A to B at 9 meters per second in 10 seconds, and then from C, and then to C at 12 meters per second in 5 seconds. What's the average speed and average velocity? So the person traveled like this, and then like this. Okay, so you know the V is D over T. This is speed. Speed is distance over time. Distance is VT. So right now, I'm more interested in finding out what is the total distance traveled. This one will be 9 times 10, giving me 90 meters. 12 times 5 will give me 60 meters. I need this in order to calculate out my average speed. Right now, my average speed is the total distance divided by total time. So right now, it should be 90 plus 60 divided by 10 plus 5. So 90 plus 60 divided by 15 gives you 10 meters per second. Now, on the other hand, if I wanted to find the average velocity, it will be total displacement over total time. But my displacement here is actually this one. Okay, this part here is my reference point. Okay, this is my end point. I'm talking about the distance of this point from this reference point in this direction. Okay, so my displacement is this green colored line here. Now your displacement here, you have to use Pythagoras theorem to find out the displacement. This one would actually be, since the red colored line highlighted in green here is the hypotenuse of the triangle, this one will be 90 square plus 60 square, square root of that, you're gonna get 108 meter. So your total displacement here is 108 divided by 15. Okay, because you took 10 seconds here, you took 15 seconds here, so you will still be taking the same time. So this one will be 15 seconds. So it'll be 108 divided by 15, giving you 7.2 meter per second. So this is average speed and this is average velocity. Now, there will be some cases where people do something like this, where they see that, oh, this is 9 meters per second, this is 12 meters per second. Can't I just use this to find the average velocity here? Some people may straight away use this, where they say that V is actually square root of 9 square plus with 12 square, giving you 15 meters per second. This is also finding velocity, but this is not going to be your average velocity though. When you do it this way, this is not average velocity. This is actually finding resultant velocity. Okay, so this method here of finding a velocity is not going to give you average velocity. It's actually giving you resultant velocity. The confusion arises because when you guys went through your first chapter to find resultant velocity, you found velocity in this way. So sometimes without doing, when people look at this question, they somehow use back this same method. This is not going to find you average velocity. This is going to give you resultant velocity. They are not the same as average velocity. Okay, so just be careful about that. All right. And then when you're talking about velocity, velocity is usually the gradient of your displacement time graph. There are a few graphs that are shown here. So let me just clear this off. Okay. If you see that you have constant gradient, if you have constant gradient, you have constant velocity. If your gradient becomes steeper from here to here, from low gradient to high gradient, the gradient is now steeper, you have higher velocity. If you have zero gradient, you have zero velocity. Your object is actually stationary here. And then after that, if you see that you have a case where your gradient changes direction, your velocity is deemed to have changed direction too. And then when you see that your gradient changes, your velocity changes. Gradient changes is when you see a curve like this. If you were to draw some little triangle along the curve, you can see that the steepness of the triangle is changing. This is what we mean by gradient changing. Okay, so that is for velocity. Now, the last term that you will use to describe motion is acceleration. Okay, now acceleration is normally used to tell you, acceleration is normally used to tell you whether an object is speeding up or slowing down. Just go out again. Yeah, okay, this is better. Acceleration will tell you whether your object is speeding up or slowing down. Okay, acceleration is just simply defined as rate of change of velocity. It's velocity divided by time, given by this symbol here. Acceleration is a vector quantity and is measured in meter per second squared. Now, because you define acceleration as rate of change of velocity, whenever velocity changes, you will have acceleration. You will consider velocity to have changed if there is either a change in the magnitude or direction. Okay. If your velocity direction changes, your velocity is assumed to your velocity is considered to have changed, so you have acceleration. If your magnitude of velocity changes, your velocity is considered to have changed, so you have acceleration. Okay. Now, specifically, you need to know what is the effect of acceleration direction on your velocity or your motion. Now, there are a few cases that are given to you here. When you see your acceleration is in the same direction as your motion or your velocity, we will tell you that your magnitude of velocity increases, but your direction of motion remains unchanged. Your object will actually speed up. Okay, this is if acceleration is in the same direction as your motion. Usually, motion and velocity are always the same. Okay, they are comparable to each other. If you say that your motion is towards the right, your velocity is also towards the right. So those two terms are actually interchangeable. If you see acceleration is in the same direction as your motion or velocity, your velocity would increase, but your direction of motion remains unchanged. Your object is now speeding up. On the other hand, if your acceleration is opposite in direction to your motion and velocity, your magnitude of velocity now decreases, your direction of motion still remains unchanged, your object is now slowing down, okay? But what happens if your acceleration is perpendicular to your motion or velocity? Mean to say something like this. Now, when your acceleration is perpendicular to motion or velocity, your magnitude of your velocity remains the same. However, your direction of motion will start to change. What we mean by that is this. If your acceleration is perpendicular to your motion or velocity like this, the acceleration will cause your velocity to suddenly turn like this. This will be now your motion direction or your velocity direction. It's because your acceleration was perpendicular to your motion. It will cause the direction itself to change, but it will not cause the magnitude to change. It will remain the same. Now, the last one will be if your acceleration is at an angle to your motion or velocity, meaning to say it is something like this. Okay. Now, if your acceleration is at an angle to your motion and velocity, you can consider two things first. You can consider that your acceleration here can be resolved into two components. There's the vertical acceleration and there's the horizontal acceleration. Now, these two acceleration components will cause two different effects. This vertical acceleration is perpendicular to your motion. It's actually similar to this case. This parallel component of acceleration in the same direction as your motion is actually similar to this case. Okay, so each of these will actually cause an individual effect. So if you just consider this one, it will cause the direction of motion to change. But if you consider this one, it will cause the magnitude of your velocity to increase. Okay, they are a combination of the first example and the third example. All right. So here we will say that the object changes direction, but with increasing speed. That's all there is to it. Usually in your exam questions, you won't go up to this level. This one, you will normally be asked about this. They will only ask as far as what if the acceleration is perpendicular to your motion. This is one thing that you need to know. It is actually inside your AS syllabus. Okay. Now, for an object that is moving in a circle at 10 with a constant speed of 10 meters per second, like this, is there any acceleration? This one is 10 meters per second. This one is 10 meters per second. This is 10 meters per second. And then that one is also 10 meters per second. So the question is just asking you, is there any acceleration here? The answer is yes, but how do you explain that there's acceleration here? Number one, remember we told you that acceleration is rate of change of velocity. So the acceleration is rate of change of velocity. This means that there is acceleration when velocity changes. Now, when you look at the object right now, the object that's moving in a circle here, the direction of velocity continuously changes. Therefore, velocity is changing. So thus, there is acceleration. Okay, acceleration is rate of change of velocity. You have acceleration when velocity changes. Right now, you see that your velocity direction keeps changing. Therefore, velocity is changing. Thus, there is acceleration. Okay. Now, if we ask you one step further, what is the direction of the acceleration? This one, you will say something like this. Since magnitude remains the same, but only direction changes, the acceleration must always be perpendicular to the velocity. Okay, So you see, when you go from here to here to here to here, the magnitude itself did not change, but only the direction has changed. Previously, in the examples that I described to you, you notice that for a magnitude to always remain the same, but only the direction changes, you must have the acceleration perpendicular to your motion or velocity. So over here, when something is moving in a circle, and we tell you that the speed remains the same, meaning to say the magnitude remains the same, only the direction is changing, your acceleration must always be perpendicular to the velocity. So what we mean by that is that over here, your acceleration is always going to be direct, always going to be perpendicular. You have an acceleration perpendicular like this. You have an acceleration perpendicular like this. You also have an acceleration that is perpendicular like this. Okay, so you see, for your magnitude to remain the same but only direction changes, your acceleration must be perpendicular to your velocity. But at the same time, you notice one thing: if your velocity, if your acceleration is always perpendicular to your velocity, notice that the acceleration is always directed towards the center of the circle. Okay, so you can also say this. Not, you can also say that not only is the acceleration always perpendicular to the velocity, is always directed towards the center of the circle. It's always towards the center of the circle. Okay. Now, in your in your A2 letter, we will actually talk more about this example again. All right. We will talk more about what is actually this acceleration, how to calculate it. This acceleration to the center here is actually known as your centripetal acceleration. It's the acceleration that causes an object to move in a circle, but it is not covered in AS. This one will be in A2. In your AS level, it's sufficient to know up to this part only. When they ask you if something is moving in a circle, do we say that there's acceleration? Yes, we say that there's acceleration. Because you have direction change, that means your velocity changes. That in turn means that you have acceleration. Okay, right. And then another thing I probably should add in here is this. Your velocity is always tangent to the path of the curve. All right, when you're moving in a circle, you want to find the velocity at any particular point on the path, it will always be tangent to it. So if I say I want to find out what is the velocity direction here, the velocity will be tangent to this point. Likewise, I want to find the velocity here, it will be tangent to this point. Okay. So likewise, the same for all the other points. Velocity is always tangent to the path or the curve at the given point. At any given point. Okay, sorry. At any given point. Okay, so this is for acceleration. Okay, so then after that, there's just some other stuff to highlight again. Now, when you're talking about acceleration, the relation with velocity time graph is that the acceleration is always going to be the gradient of your velocity time graph. So same thing as before, if you have constant gradient, constant acceleration. If your gradient is steeper, you have higher acceleration. If you have zero gradient, you have zero acceleration. That would mean that you're moving with constant velocity. Sorry, there's a missing word here. Constant velocity. Okay. When you have zero acceleration, you're moving with constant velocity. This one is important to know. When A is zero, V is constant. Okay. That means you have no change in velocity because remember, acceleration is actually rate of change of velocity. If your acceleration is zero, that means your velocity isn't changing. That means V is constant. All right. Then after that, if you move on to the next diagram, negative gradient means negative acceleration. Changing gradient means changing acceleration. So this is for this. Okay, then we go on to some other part. This one will be more related to your interpretation of the graphs. All right. Now, relationship between ST, VT, and AT graphs. You, in your exam questions, you a lot of times will be asked to change from one graph to another if given one of them. But before we can go to that, you need to know how to look at the graphs first. Now, if we tell you that velocity is rate of change of displacement, this means that the value of V is equals to the gradient of your ST graph. Likewise, if we say that acceleration is rate of change of velocity, the value of acceleration is equals to the gradient of your VT graph. Okay, so what do we mean by this? This one will be more in the next example, but before I go through that, let's just look at these four graphs here. Now, I want to describe this graph in terms of two things only. In terms of its gradient and in terms of its value. If I want to describe this first graph in terms of its gradient, I would say that this graph is less and less positive. Okay, it is positive because it's pointing upwards. It is less and less positive because you notice that it's becoming less and less steep. So we call this less and less positive. But when we talk about the value of the graph here refers to the y-axis value. Okay. Now, all the values that you have here on your y-axis are positive, but you see as you go along the graph, what can I describe? How can I describe the value of the values? How can I describe the values? The values are actually becoming more and more positive. It could be that maybe this is positive 2, positive 4, positive 6, positive 8. They are all positive, but they're becoming more and more positive. All right, this is one way in which you can describe a graph. Here we say that it's less and less positive for gradient, and then the value is more and more positive. All right. So what about if I talk to you about the second graph here? Because this graph is pointing downwards, I know that this graph is negative. But how will I describe the gradient in terms of its steepness? You notice that you draw some little triangle along the curve. It's actually becoming more and more steep. So here we say that the gradient is becoming more and more negative. But in terms of the values of the graph itself, looking at the y-axis value, this is all positive. Okay. But how do I describe this? I mean, I'm going from here to here to here. The value is becoming less and less positive. It could be that from positive 8, I will go to positive 6, and then subsequently going to positive 4. This one is what we say is less and less positive. Then you look at the third graph, this one again. This one, the graph is pointing upwards. So it's positive gradient, but you notice that it's becoming more and more steep. So it's more and more positive. But then when you look at the values of the graph, the values in the y-axis, this is all negative. Your values would be negative, but then you look at how the values are changing. From here, you go to here, it goes to here, it goes to here. From this point to this point to this point to this point. It's actually becoming less and less negative. It could be from negative 8 going to negative 6, negative 4, negative 2. So this is less and less negative. Okay. Then the last one should be more straightforward. This one is negative graph, but gradient is constant. And then you want to describe the value of your graph, it is still negative, but looking at how it's changing, you will notice that the values are becoming more and more negative, maybe from negative 2 to negative 4 to negative 6. So this is more and more negative. This is how you describe the variations in the graph. You need to know how to describe these variations of the graph before you can interpret the graphs, before you can start changing it from one form to another. The example will be in the next page. All right, so let's go through that. All right, now if you look at the first example here, say right now I give you one graph, this graph, okay, and I want you to produce the ST graph and the AT graph by looking at this graph itself. I will need to look at the gradient as well as the value. But before I go through that, recall that we mentioned that velocity is rate of change of displacement and acceleration is rate of change of velocity. So from here, we say that the value of velocity is equals to the gradient of your ST graph. Likewise, the value of your acceleration is equals to the gradient of your VT graph. So right now, let's just go with this. How would I describe this gradient? This gradient is positive and constant, right? Okay. Let me just write it up properly. This gradient is positive and constant. Okay. Right. Gradient of VT. Let me just write this gradient of VT, gradient of ST. Okay. So the gradient of your VT graph, this one is your VT graph. Okay, this is your VT graph. The gradient of your VT graph gives you the value of your acceleration. Right now, you see this one, the gradient of your VT graph is positive and constant. So what this will tell you is, therefore, A is positive and constant. Therefore, your shape of the graph is this. It is positive and it is constant. This is for acceleration. Now, if you want to then use this same graph to give you your ST graph, you need to use this relation here. This one is telling you the value of your velocity is equals to the gradient of your ST graph. Okay, so right now you look at the value of your velocity. Again, look at the y-axis value from here to here to here. How will I describe the values? This one, I will say that the value is more and more positive. So likewise, you can say that the gradient of ST is more and more positive. Okay, which gives you this graph instead. If you look at this graph, you can clearly see that the gradient is becoming more and more positive. Okay, so this is one way of changing the graph. So if I move on to the second example, same thing as before. I start with your VT graph, and then I want you to produce your ST as well as your AT. So looking at this one, how would you describe the gradient of your VT graph? This one, you can describe your gradient as being, let me just wipe off all this because it's in the way. This one, I can say that the gradient is negative and constant. So likewise, you can say that therefore A is negative and constant, which in turn gives you this. But if I want to describe the values again, this point here going to this point here, going to this point here, all the values here are still positive. But the way I will describe the value is that the value is less and less positive. Therefore, maybe I just write this. Therefore, gradient of ST is less and less positive. So you could end up with either a graph like this or either a graph like this. Notice that both graphs have gradients that are actually less and less positive. Okay. Now, this will only tell you how the gradient of your ST changes, but it won't tell you whether your gradient values are going to be positive or negative. This one you will know. There's not enough information for you to determine that, but what you do know is that you're able to determine the variation of the gradient of your ST graph. Okay, so that's why I give you two different graphs here. It could either be this or it could either be this. You won't know whether it's positive displacement or negative displacement. You just know that the gradient looks like that only. All right, so that one is okay. Right. So whatever little statements that I wrote out here individually is actually the same statement that you've seen being written here. Okay, right? Then the last example would be this before we go to one example in your past year. So let me just erase everything. Okay, so let's go through this last one. How would I describe this gradient? It's pointing downwards, so it's negative. So I can say that the gradient is actually becoming less and less negative, isn't it? Because you see it's becoming less and less steep. It's less and less negative. So therefore, A is less and less negative too, which will give you this. Either you can say it as this or this or this. Okay, because I'm only concerned with the value, right? This one is giving me negative values of my A, but it doesn't tell me how the values are changing, how the gradient of the AT graph is changing. I only know that the value is becoming less and less negative. So it could be this graph, or it could be this graph, or it could be this graph. Okay, either one is actually correct to describe the variation. Okay, so this one is for gradient, but then now if I want to go to the values, this one you see all the values are negative. The values are becoming more and more negative, right? So this one, the value is more and more negative. So the next thing I'll say is therefore gradient of ST is more and more negative, which again gives me something like this. I can have two possible choices. I do not know whether the displacement will always be positive. I do not know whether the displacement will always be negative. You just don't know, but you do know that the gradient variation is like this, okay? So in some cases, you will get two possible graphs for ST and AT graphs for the examples above, like the ones that I showed you here. You can get two or more graphs for the same graph type. Okay, so this is how you would deduce out your shape of your motion graphs. All right, so let's go through one example. Okay, if you go to your kinematics worksheet, there's one or two graph drawing examples that we can go through. That one we can go have a look at page 29. If you were just to look at page 29, okay, this one will make use of what I just mentioned to you. Okay, have you done a question like this before?
Yeah, something similar in school.
Okay, so how will you get the answer for this? Right, let's just see this one. Okay, now just now the methods that I mentioned to you, you can try and apply it for this example here. Okay, just that you use this one. Wait, let me. Okay, they tell you that the graph here shows how the velocity v of an object moving in a straight line varies with time t from 0 to capital T. Which graph represents the displacement s of the object in time 0 to capital T? All right. So how would you do this is that you, in my case, normally we would just do the methods that I use, where I tell you that velocity is s over t, a is v over t, or right now because I only have vt and st, I'm just going to use this one. Okay, this one I know that the value of v is equals to the gradient of my st graph. So this graph that you see here, you can actually describe the motion in 4 separate parts. You can split this out into 4 separate parts like this. This one is section 1, section 2, section 3, section 4. So I want to convert it from Vt into St. So the relation now is between velocity and displacement. This is the relation that you will use. Right now here you see that the the value of your velocity will give you the gradient of your st graph. So like in my case here, if I want to describe the value of the velocity, let me just rewrite it here. This one, maybe it's better if I use dots. Okay. From here to here to here, this one I can say that the value of v is becoming more and more positive. So I can say that therefore gradient is more and more positive too. Okay. But then if I talk about this part here, I would say that the value of v is less and less positive. Therefore, gradient is also less and less positive. Then if I look at this one I will say that the value is more and more negative. Therefore, gradient is more and more negative too. And then lastly, if I say, maybe I should use this one. If I say this one, this side here, my value is becoming less and less negative. So I can say this. Therefore, gradient is less and less negative. So this is what I can see. So which of the graph shows you that? It's actually supposed to be A, because you see, if I were to divide this into 4 separate sections, like the ones that I showed to you here, 1, 2, 3, and 4, just look at how the gradient is changing. You see, this one here, the gradient is positive and it's becoming more and more positive, isn't it? You see, this one is becoming more and more positive. You draw some little triangles that you can visualize it as becoming more and more positive. This is going to be this one here. Sorry. Okay. This part here will correspond to this. Then if I look at the other one, this shape here, the gradient is also still positive, but notice that it's becoming less and less steep. It's becoming less and less positive. This is actually describing this. And then you look at the other one, like this one. Now you have negative gradient, but you notice that it is becoming more and more steep. The gradient is becoming more and more negative. This is actually this. And then the last one would be this one. Again, it is a negative gradient because it's pointing downwards, but you notice that it's becoming less steep. This is becoming less and less negative. It is going to be talking about this. So this is actually the correct displacement time graph for the given graph. Okay.